All right.
Okay, let's go.
Well, good evening, everyone. And on behalf of Dimitra and the Center for Space Science and Srini, we welcome you, and especially to our speaker, Dr. Luju Ojha, Assistant Professor at Rutgers University. He'll be speaking to us tonight for a very special webinar in light of the arrival of the HOPE probe to the Mars orbit this evening in where we're celebrating here in the UAE. So Dr. Ojha is currently at Rutgers University, and he's a planetary scientist. He's been involved in NASA's MRO and InSight mission. And tonight he is going to present to us some of his research that we very much look forward to hearing about. Thank you very much for joining us, Dr. Luju.
Thank you for having me.
Yeah, thank you for having me. It's a very exciting day, and thank you, I guess, everyone who was here listening to me talk instead of watching all the exciting media coverage of the HOPE mission. And those of you that are involved with the HOPE mission, really, congratulations. That's a great achievement. And I'll be watching in about an hour after this talk ends too. So I'm hoping everything goes right. United States, in 1 hour, we have the impeachment trial. You guys have the HOPE mission. I mean, yeah, exciting time.
The two are equivalent somehow.
Just a difference of two worlds, I guess. But thanks for having me. And I thought when I got the invitation, I was kind of looking at the NYC Abu Dhabi roster, and it looks like there's a lot of astronomers, astrophysicists, and also some Mars people working there. So I thought I would present on something that I had been thinking about for a while, but I recently was able to get the work completed and publish a paper. And especially if there's any of you involved with the HOPE mission, I hope you maybe think about some of the implications of this work going forward with HOPE mission. All right, so I'm going to share my slides here, and it's let's see, there we go. Cool. So now you should be able to see my screen.
Yep.
Sweet, awesome. So right. And again, if there are any questions about the work that you wanted to ask, but you didn't get time for whatever reason, please, you can always email me at my Rutgers email, or you can just go to my website and contact me through there. Okay, so so today I'll talk about what's called the faint young sun paradox on Mars and potential solution. Or at least the solutions that I think might be able to solve this paradox. So let's first learn about the paradox. Before that, I just wanted to point out that this is a work that was not possible without some of my collaborators. So the entirety of the talk is going to be based on basically results from two papers. The first one is this that came out in Science Advances a couple of months ago. And I've left the information here. And then the second paper that's in press right now at Nature is the following paper. And so again, just wanted to acknowledge my collaborators at Johns Hopkins, Dartmouth, PSI. And so anyways, all right. So our sun is a typical star in the main sequence, right? And in these sort of stars, the primary reason that there's luminosity is this sort of, hydrogen to helium fusion happening, right? And so the fusion, so when you think about the stellar life over time, that sort of hydrogen to helium conversion happens at an increasing rate over time, right? And when that happens, your molecular weight of that core, because you're going into a heavier state, increases, and so therefore the core has to contract over time and warm. And so if you were to just sort of model the standard evolution of a typical star over time, what you find is that the total output from the star, which is the the luminosity changes, right? Especially when you're talking about 4 billion years, right? We're talking about the evolution of planets and its sort of co-evolution with stars in the last 4 billion years. So if the luminosity, or the sort of like the total brightness of star, is 1 today, 4 billion years ago, our sun would have been about 70% as bright. And so the reason that this thing is called faint young sun is, again, because this idea from standard stellar evolution models posits that 4 billion years ago, the sun was relatively younger and much fainter. Okay, so that's the faint young sun. Now, the faint young sun has a lot of sort of implications for the evolution of planets. And so the work that I'm at least aware of, the first work that talked about the implication of this stellar of faint young sun to planetary climate, is from Ringwood 1961, where you can see this text highlighted in yellow, that between 4.5 billion years ago and 3 billion years ago, Earth should have passed through an intense ice age. Okay, and you can see that sort of plot here in the right too, where 4 billion years ago, doesn't matter how much you put CO2 and H2O in the atmosphere, the temperature should have been relatively small, right? Not enough for water to undergo melting and remain sustainably in a liquid state. Of course, you can add some other greenhouse gases in the atmosphere and let go of the problem, right? But this is kind of like the fundamental sort of messes of the faint young sun paradox, or the fundamental problem with the faint young sun paradox is that the sun was faint, and you need to somehow elevate the temperature of a planet using some other mechanism. But we know that 4 billion years ago, at least on Earth, from rock record, especially these what are called zircon grains from Hadean time, which is approximately 4 billion years plus. Through oxygen isotope, we know that there was liquid water on the Earth's surface. And so you can look at this paper, for example. This is just one of the paper, right? We also know, even going back 4.4 billion years ago, from these zircon grains again, and via oxygen isotope, that there was liquid water 4.4 billion years ago. And so, this has led to sort of this back and forth between whether there was a faint young sun paradox for the early Earth. Earth is, and there are papers every once in a while where the entire idea of faint young sun seems to have been solved. But then you get other papers like, now the faint young sun paradox remains. But most of the solution for the faint young sun, again, comes from, what sort of atmosphere would you need when you have 70% luminosity of the sun for Earth to have had liquid water? And there's mostly atmospheric solution, but there's also solutions that, for example, this paper here, faint young sun, planetary paleoclimates and varying fundamental constants. In this paper, a radical idea is that these sort of physical constants we think about, like gravitational constants, have actually changed over time. And so that is a proposed solution, right? So there's a lot of different solutions. There's a lot of back and forth, and I will not talk too much about Earth because I think the problem is way worse for Mars. And so the sort of same problem that plagues the early Earth plagues Mars to a rather maybe additional level. Right, and that is because Mars is farther than Earth. That's 47 million miles away, and only about 43% of the solar flux that Earth gets is what Mars gets. So, provided that for some reason that Mars wasn't closer to the sun than it is now, the early Mars, 4 billion years ago, the climate of Mars should have been extremely cold. And a lot of people that are in the atmospheric field, they've run state-of-the-art 3D atmospheric model just to see how cold are we talking about and if there is a solution. what's called the equilibrium temperature of Mars, which is if you assume that Mars is a perfect black body, right? In other words, it is absorbing 100% of the radiation incident on Mars, absorbs it, and it's like a perfect, emitter with emissivity equal to unity. Then the equilibrium temperature is about, I think, like close to 195 Kelvin. Okay, so that means that somehow 4 billion years ago, you need to put gas in the Martian atmosphere so you can have additional 78 Kelvin or so of greenhouse warming. Okay, so that's the sort of like the rough number is about 78 Kelvin of warming due to greenhouse effect. And so you can now start putting in various amounts of water, CO2, SO2, or ammonia, right? Methane. You can think of your favorite greenhouse gas, and you can start doing this experiment a little bit. And this is, for example, one of the plots from a paper that does similar thing, where in this case they crank the Martian atmosphere with water and CO2, and they assume that it has 1 bar atmospheric pressure. 4 billion years ago, and it shows you the temperature as a function of latitude, right? So this is -90 being North Pole, -90 being South Pole, 90 being North Pole. And so these are the annual mean, and then the average, the maximum temperature over in those latitude regions. And so while, with 1 bar atmospheric CO2, you could potentially get these extreme insolation-related, obliquity-related temperature max, you never get a consistently stable mean annual temperature that even remotely approaches 273 Kelvin, which is where, water goes from solid to liquid state. Now, one may make an argument saying that, well, this is only assuming 1 bar atmospheric pressure of CO2. Let's crank it up, right? Let's put 5 bar of atmospheric CO2 for all we care. The issue that happens is as you start putting more and more CO2 in the atmosphere, at about 2 bar, your atmospheric CO2 starts saturating. And then after that, you don't really have any net increase in the temperature. Instead, all the CO2 starts precipitating out of the atmosphere. Okay, so there's a limit to how much CO2 can you put in the atmosphere and still be able to raise the temperature. And that limit turns out to be about 2 atmospheric bar. And after that, you're just going to get precipitation, supersaturation of CO2. And even with 2 bar atmospheric carbon dioxide, the temperature is still not high enough for liquid water to be stable. And again, the point here is not that you can't get these extreme fluctuations every once in a while in some region, but it's the idea that was Mars 4 billion years ago long-term warm and wet, or was it characterized in this sort of like long-term as a icy planet? Okay. And so, but we know when we look at the surface of Mars that there was a ton of liquid water that interacted with the surface. We see what are called valley networks, which superficially resemble water on Earth. Right. Here you can see this, a typical example of valley network where you have multiple sort of channels and then their tributaries, right? It's got a dense network. If the word Strahler order means anything to you, it has a Strahler order of about 7. If that word doesn't mean anything to you, it just means that it has multiple child, right? If you think about this as a tree, that, this tree has multiple branches, multiple kids, okay? And so this is a very telltale sign that, there was liquid water interacting on the surface of Mars 4 billion years ago. Here's another channel, right? In this case, this channel is 40 kilometer wide, right? So from one side of the channel to another, that's about 40 kilometer wide. And I would guess that if you're on the surface of Mars, you wouldn't be able to see the other side of the channel. I mean, that's how big it is, right? So if you think about the biggest rivers on Earth, where can you find a channel? Where can you find a river that is 40 kilometer wide? This figure, I made this so I know that there's about like 3:1 vertical exaggeration, but there is no, horizontal exaggeration. That is really 40 kilometer. And so again, how do you form these sort of channels under this problem of the faint young sun? Here's another channel, again, a 3D view, and you can see this channel actually flowing all the way and then opening into a crater, much like the situation in Jezero crater, where the NASA Mars mission will be landing in about a week or so. And just another eye candy, again, you can see these rather long channels. This channel, in this widest space is about 20 kilometer and hundreds of kilometer long. And these channels are kind of everywhere in the Southern Hemisphere. So this is a map that shows the geographic distribution. So the background is kind of like your standard map atlas, if you will, right? Olympus Mons, the tallest volcano in the solar system, is right over there. Gale crater is right over there. The InSight spacecraft is over there. The MSL spacecraft is over there. Jezero crater is over here, where the new Mars rover is going to be landing. And you can see all the places with those red dots. That's where we have valley networks on Mars, right? So these, again, these river-looking channels, and you can see that they're mostly in the Southern Hemisphere. And so not only the sort of like, photo interpretation for liquid water, for evidence of liquid water in Mars's past, but I mean, via doing what's called spectroscopy, where we basically look at the surface of Mars and different sort of, range in the electromagnetic spectrum, anywhere from, gamma ray up to thermal infrared. And by understanding how lights interact with materials of different composition, we can figure out what is present on Mars. And so you can see here again, similar map. The background gray map shows you kind of like the atlas of Mars. Sorry. And you can see the distribution of phyllosilicates, your typical clay, for example, hydrated silica, chlorides, which in a lot of sense requires some sort of groundwater, carbonates, and then sulfates. Okay, so the point again here being that the Southern Hemisphere again is not only there's not only a plethora of evidence from spectral work that there was tons of liquid water interacting with the ground, but also we have tons of evidence from valley network that there was liquid water and terrain interaction. So this brings us to, this idea that, most of these, again, so this is the map of Earth and map of Mars. And so the way we date the planetary surface on Mars is via impact crater dating. And so this Noachian time, which started about 4.1 billion years ago and ended around 3.5, this is where most of the geological activity that require liquid water. Most of the geological activity happened around this Noachian time. This is when we see most of the clays on Mars, and this is also where we see most of the valley network on Mars. And so this is what's called the faint young sun paradox on Mars. Okay, so it's a paradox between the geological evidence that suggests that there was tons of liquid water, and then climate models that really struggle to elevate the surface temperature past the melting point of water ice on Mars. So again, we see all these geological evidence that there was water, via spectroscopy or valley networks, but then when we run the climate models, it's really hard to overcome how you can do that. And so far, this attempt to solve the faint young sun paradox in Mars has primarily focused on greenhouse gases, like the gases, like I said, like, CO2, water, sulfur dioxide, methane, etc. But every single of these gases have sustainability issues that are yet to be solved. And so much so, and this debate is so much so that there is an entire editorial piece in Nature Geosciences, and the editorial piece is called Mars at War. And I just wanted to point out one, I think, funny line from this article. It says that if one stumbles into a conference on early Mars, it quickly becomes clear that the battle lines are drawn. On the one side, scientists argue that early Mars was warm and wet. On the other hand, they visit that it was cold and dry. So so much, there's so much debate, I guess, on this topic that there's an entire article called Mars at War about the fight between the scientists from the two opposite ends. And so basically, this is the two opposing views of early Mars. One that at least I was most familiar with when I was in school, and it's this idea that Mars could have had this northern ocean. Mars could have had this like open liquid water, just like Earth, no problem. But then there's also, there's a lot of problems with this view of Mars, and then there's this view that, no, there was no such thing as this northern ocean. There was no, long-term warm and wet Mars. It was primarily characterized by this icy Noachian highland terrain. So in this case, most of the snow, which is shown in white, most of the snow and ice gets deposited in the southern hemisphere because it is higher in elevation. So because of the adiabatic cooling, just like on Earth, as you go higher and higher up in elevation, you have more and more of snow and icefall deposit. And so these are the two opposing end members. And again, trying to come up with a solution has mostly focused on gases, atmospheric gases, but they all have sustainability issue. And anyone who is interested in that, I would point out to these three papers that do really good comprehensive work. The paper by Haverly et al., they actually really go into depth about problems with some of the greenhouse gases. And so my solution was the following, that, we're not going to go through the atmospheric solution because that has been done so many times, but we are going to look at a different kind of solution, perhaps what's called a geophysical solution. And so here in this case, you can imagine that if Mars was primarily cold and icy 4 billion years ago, you have some surface temperature coming from the sun that's too low to melt any ice, right? But there could have been a situation where the internal heat generated from Mars by Mars via radioactive decay of heat-producing elements could have been high enough for one to get what's called a basal melt. So here, the melting of ice happens from bottom heat, right, bottom up, rather than top down. So that's why this is called basal melting. And this is not something weird or unique for Mars. This is something that we see on Earth all the time. So underneath the thick ice cap of Antarctica, we see what's called subglacial lakes. So here in this region in the Western Antarctica, you can see all these subglacial lakes where liquid water can exist underneath the thick ice cap because of high geothermal heat. All right, so every time you see these sort of blue area, these are subglacial liquid water lakes. There are also not only just lakes, but there are channels, subglacial channels under these thick ice glaciers in Greenland. And these channels, in a lot of ways, tend to resemble what we see on Mars, these valley network looking channels. And again, these sort of subglacial water carb networks are in some cases mostly driven by geothermal heat. And recent work has also looked at these valley networks in Mars and concluded that a substantial amount of these channels of these valley networks that we see on Mars, they resemble these sort of subglacial channels more than channels that were formed by freely flowing liquid water. Okay, one of the hallmark of the subglacial channel is that they tend to flow uphill. So if you think about water, if you were to just pour down a glass of water, water always flows downhill, right? That's the conventional wisdom. But what happens under a thick ice glacier is that you have so much pressure from the overhead, the overlying ice, that that depending on the topography of the ice, the flow route is dictated by the topography of the ice. So there are many cases where these sort of what's called tunnel valleys, for example, they tend to flow uphill. Okay, and so in this work, they looked at the slopes of a lot of these channels we see on Mars, and one of the thing that they've noticed is that there's a lot of channels on Mars that tend to be flowing uphill, which doesn't make conventional sense with the way we know how water flows. And so, and there's also a lot of evidence of this sort of, water generated by internal heat from spectral work. And so this is a paper from 2011 where they found a lot of these clay minerals and other hydrated minerals deep on the subsurface of Mars. And so, these clays were found from like impact ejecta from these deep craters. And there's also some minerals that we found on Mars, like serpentine, for example, or prehnite, that argues that not only do you need water, but you need water that is really hot for these minerals to form. And so overall, there seems to be this sort of new way of thinking about like Martian water in the past, and the emerging view might be that there was substantial amount of internal heat generated by Mars that allow liquid water to exist. And so this idea is also appealing because 4 billion years ago, the key radioactive elements like your potassium, your thorium, your uranium, the amount of heat production would have been higher because there would have been a higher concentration of these elements. Right? These elements have half-lives of billions of years. So 4 billion years ago, because their concentration was higher, the amount of heat generated would have been exponentially higher too. And so you can see different isotopes of potassium, thorium, uranium, and you can see the total production power over time. Okay, so that's another reason. And so what we said was, okay, let's consider this as a non-divisive solution. So if Mars was primarily wet, then that's fine. Then that's fine. All our work means is that then there could have been vigorous sort of hydrothermal circulation in the subsurface. However, if the other view of Mars is correct, where Mars is characterized mostly by this cold, icy highlands, then our idea of this geothermal heat flux might be the only way to create liquid water on the surface and explain valley networks, or explain clay, and explain other evidence of water on the surface. And so there's a lot of detail into the modeling, how we did this, but basically it's a one-dimensional finite element model where the thermophysical constants related to the ice, specifically its density, its thermal conductivity, changes not only as a function of depth, so rho here being density. So not only is that density changing with depth because of compaction, right? You can imagine if you put like 2 kilometers of snow, it starts compacting over time. But that change in density also leads to changes in the thermal conductivity of the ice. But there's also a time component where the compaction of the ice and snow happens over time. And so that dictates how the ice evolves over time. And then we have these thermal models to predict not only if melting occurs, but also how much melting occurs. And we do that by this enthalpy method, right? And so this allows us to, again, quantify the amount of basal melt you can get by this internal heat. And so you can find the details of this model in this paper, but I won't talk about the model too much. I'll just show you the results. And so basically what we found was, again, we wanted to see how much melt could you get for a given thickness of ice and given surface heat flow. And so what we find is that in general, you need Mars 4 billion years ago for it to have undergone basal melting. You need at least 55 milliwatts per meter square of heat flow, right? And so these color plots, they show ice thickness of different height and also over different times. So 1000 Ka being like 1 million year. Over 1 million year, if you only had 55 milliwatts per meter square, you could get basal melting of about 100 meter from a 2000 meter thick ice cap. Okay, so as you can see that there's a lot of variables that will play a role in whether basal melting is possible or not. So one of them is the snow accumulation rate, right? How far is the snow accumulation happening, which is given by B. The other one is H tot or H total, which is basically how thick of an ice cap could you make? Because the thicker the ice, the more you are able to insulate heat. And also then the other factor is the time, right? The longer you let the model run, the more basal melt you're going to get. And then certainly, perhaps the most important factor is the QS, which is the surface heat flow you would require for basal melting to occur. And so essentially what we found in this preliminary sort of exercise is that you need at least 55, and the higher the heat flow, that's better. And so what does this number mean, right? If you've never seen surface heat flow measurement, you're basically, so the way we find that out on Earth is by drilling to significant depth and seeing how much heat is being generated from the interior. And so here's a surface heat flow map of Earth, right? And you can see a lot of diversity in the surface heat flow values. So this is just for, the North America here in this case. So where I am in New York, there's not a lot of geological activity going on. It's a passive plate, it's a passive margin. So the surface heat flow is relatively low, about 20, maybe 30 milliwatts per meter square. But if you go to places like the Yellowstone, right, where we know that there's an intrusion, we know that there's this active sort of hydrothermal system, there you can get heat flow upwards of 200 milliwatts per meter square. And then again, in the sort of like the Pacific plate down in the down in the oceanic crust where new crusts are being made, you can get heat flow that exceeds 1,000 milliwatts per meter square. Okay, so just to give you a sense of what these values mean, that typically on Earth continental crust, if it's an active sort of geological region, then you can get upwards of 100, 200. The only other planet where we've made this sort of heat flow measurement is only other body, I should say, is the Moon, where we got a heat flow. We measured heat flow in the Apollo area, and it was about 15 milliwatts per meter square. The InSight spacecraft on Mars was supposed to make that measurement, but that measurement was never made because of the instrument difficulty with the instrument. And so, so then, how do we even compute the heat flow then, right? I mean, we don't have a driller on Mars now, so how do you compute the heat flow? Well, we can certainly model whether the heat flow required for basal melting would have been possible on Mars. There's going to be caveats, there's going to be uncertainty, but we have a lot of remote sensing data. We have geochemical data, geophysical data, so we can at least provide a first order estimate of whether that sort of heat flow would have been possible. This is sort of like the very sort of simplistic model that we took where, you can divide any planet, Mars, Earth, it doesn't matter, into sort of like 3 separate regions, which is the crust, your upper mantle called lithospheric mantle, and then the lower mantle, right? And this is what's called basically your silicate fraction of the planet, where you have a significant amount of silica. Below lower mantle, you have the core, and the core is primarily iron-related mineralogy, right? So this is where most of your silicate fraction lies, and this is also where we think, at least in the case of Mars, that most of your heat-producing elements, like your uranium and its isotopes, 238 uranium, 235 thorium, and potassium will be present. And so this is a little bit of a nasty equation, but it's basically dependent on the concentration of the uranium, of the heat production from uranium, the half-life, the density, and the thickness of the crust. And this is only giving you the crustal heat flow. So one of the great things about some of the remote sensing instrument we have on Mars is that we know how much thorium and potassium there is on the Martian surface via what's called gamma ray spectroscopy. So in the spacecraft MGS, Mars Global Surveyor, there is this detector, gamma detector, and the gamma detector is able to detect the gamma ray emission from both interaction of cosmic rays with elements that are present in the soil, but also gamma ray that are naturally radiated by radioactive decay of elements like thorium and potassium. And so here you can going to show this concentration map of thorium. So this is in parts per million, and this shows the amount of thorium that is present in the Martian subsurface, right? So this is going from the surface to about 1 meter to 2 meter depth. And so again, you can see quite a bit of heterogeneity. South of 60 degrees, what happens on Mars is because you have a lot of ice, subsurface ice, that tends to dilute the signal. And so we use a mask to basically block out areas that are too polar. but this is essentially what you get. For thorium, this is potassium. And again, you can see that there's, there are places that are super enriched, and then there are places that are sort of super depleted. Some of these places that are in super dark blue. But again, the point being that we have pretty good resolution data, enough at least for this work. And then the uranium we get from a cosmological relationship, because one of the detector in the gamma ray spectrometer is sensitive to, there's I think rudium or something in the spacecraft, and so it can't predict the amount of uranium at a very good rate. Now, the other sort of parameters that we need for something like this is our idea of like how thick is the crust of Mars and how dense it is. Fortunately, we can rely on gravity data. So I love working with gravity data. And one of the things we can do is use gravity data and the topography together to come up with a crustal thickness estimate. And the details of that, I'm more than happy to talk to you at some other time. But essentially, you remove the gravity that's coming from the surface of the Mars, and you assume after you remove the surface component, right, the topographic component of the gravity, the rest of the gravity is coming from some sort of density anomaly at depth. And so then you can what's called downward continue the gravity data to the crust mantle layer, and then you can come up with a crustal thickness map like this. Okay, so we got the crustal thickness, which is your TCR. Now we know the rho CR, which is the density of the crust of Mars. And luckily, we have all these Martian meteorites, so we can actually compute, we can actually measure their density, right? To those of you that may not be familiar with these density values, the density of ice is about 900 kilogram per meter cube. So obviously, these Martian rocks, they're super iron rich, they're basaltic, they're going to be dense. So they have a density about 3,000 plus. And we also gravity from, constrained on the density from gravity data, and you can see sort of global scale heterogeneity in the density, where the southern hemisphere is relatively less dense and the northern hemisphere is relatively much more dense. Okay, but again, the point here being that we have all the geophysical and geochemical data to come up with a first order estimate of heat flow. And so this is the heat flow just from the crust about 4 billion years ago. And there are places that are really enriched in uranium, thorium, and potassium. And you can see here in this sort of like southern region, this is called the Terra Cimmeria region. And we tend to, we see relatively higher heat flow here. But again, this is nowhere close to melt ice by itself. So we need additional contribution from deeper within the Mars. And this is just for a comparison, this is the present day heat flow estimate. So right now, if you were to go to Mars and drill and try to get heat flow estimate just from the crust, you would probably see somewhere between about 3 to 4 to about 12 milliwatts per meter squared just from the crust. 4 billion years ago, the amount of uranium, thorium, potassium would have been higher. So that's why 4 billion years ago, you see this relatively higher heat flow. But still, it's not nowhere close for ice to have undergone melting, right? You need at least 55 milliwatts per meter square for melting to have occurred. So we need added contribution from inside the planet, right? So, and I was saying that there's, the QM, which is the heat flow from the mantle, from the upper mantle, but also the lower mantle. And, how do you even think about measuring something like that on a planet that is, millions of miles away, and we don't have any sort of seismic array to do that, or a heat flow probe to do that. And so we had to be a little bit creative. And so we did what's called, we use the principle of isostasy. So you can imagine that, in a planet where your outermost layer, which is the lithosphere, if it's really thin, right, and you add a mountain on top, it's going to bend. It's kind of like, if you're a big dude and you go stand on a swimming board, right, and you're trying to jump, right, if your mass is high, that board is going to bend, right? But if you're a relatively small person, skinny person, and you go and stand on a jumping board, on a diving board, I mean, that board is not going to be flexing as much, right? So it's the same principle here, that if you put a big mountain on a thin plate, then it should bend. And this is a great principle to apply on Mars, because by measuring how much the plate has bended, we can come up with the internal heat flow. Because if you have super high heat from the interior, which is the Q here, what happens is your plate has to be relatively thin. But if your heat is super low, then most of your outer portion of the planet is going to be solid, and doesn't matter how much stress you put on the top, it's never going to bend, right? So here you can see the bending, the elastic bending of the lithosphere. And in this case, where your lithosphere is super thick, you don't get as much bending. And again, the magnitude of this bend is dependent on how much heat you're generating from the inside and how much pressure you're putting by this load. And so this is a great thing to apply at Mars, because, as you know, that there is this massive North Polar cap on Mars. And so here's a view of the North Polar cap. It's volume-wise like half the volume of ice you see in Greenland, right? So massive ice deposit, mostly water, and almost like 95% pure water. So we know, how much stress it puts on the lithosphere. So a little while ago, I had used gravity data to figure out the density of this North Polar cap, and also calculate like how much stress it puts on the lithosphere. And so we were able to find out that it puts an average about 10 megapascals of stress on the lithosphere. And the really remarkable thing is that despite putting that much pressure, when you look through the radar data, so this is the North Polar cap of Mars, and what you're seeing here is basically an X-ray scan, okay? It's showing you all the different layers that were deposited as a part of, as part of the process that made the NPLD, the North Polar layer deposit. It's called layer deposit because you can see these individual layers that may be tied to Mars's climate fluctuation. But the remarkable thing is that at the basal contact between the North Polar cap and the lithosphere, you see no bend, right? You see no bend. So if you look at the surface here, there's absolutely no bending of the lithosphere. And so in this sort of earlier paper, Phillips et al., 2008, they concluded that this lithospheric deflection is less than 100 meter, which means that this lithosphere is extremely thick. And so we know now, so we know now how much stress is being put by the North Polar cap. We know that there's zero deflection. So we can run models to find out what Q or what internal heat flow would you need for there to be this massive ice cap and still see no deflection. So we ran some finite element models. And what we found in general was that this internal heat, this heat number has to be about 10 milliwatts per meter square. And so, this is the present day constraint. This is happening now. This is the observation of now, but we can scale this for 4 billion years ago again, because again, the heat being produced, it would have been higher in the past just because of the radioactive decay. And so we can back out again, similar like this, and calculate the Mantle heat flow. Sorry, going back and forth here. Sorry, there we go. So about 4 billion years ago, the Mantle heat flow would have been, easily about 30 to 40 milliwatts per meter square. And so here, this dashed line shows you the QM as a function of time. Okay, so this being the present at about 4.5 billion mark. And as you go back in the past, you can see how that number would have scaled. And so the reason that we're really doing this convoluted sort of way of figuring out all these heat flow estimates is, again, to see if, heat flow in the past could have been high enough for basal melting to occur. And so, once you get constraints from all these different parameters, including lithospheric heat flow, crustal heat flow, what we find is that there are places on Mars where the heat flow should have been at least like 70, 80 milliwatts per meter square. And so we take these sort of heat flow maps, put it in our, in our algorithm, and find out where you could have produced water by basal melting. And so let me just go to the result here. So this showed you as a function of latitude and longitude, how much water could you have produced by basal melting? So the color here shows you the amount of water you could have produced. And you can see that I blocked out significant portion of Mars here. And that's because all of these areas that are blocked out here are younger than 4 billion years, right? So these are what's called Hesperian and Amazonian. And we are primarily focused here. The main goal here is to see that, how much melt could you have formed by this process 4 billion years ago, when we see most of the evidence of these phyllosilicates, clays, and valley networks. And so this is the map of the melt. Again, so this is water that is produced by basal melting of thick ice caps. Okay, so in some cases you see, very little, like maybe like 10 meter of melt. In some other cases, you find upwards of 600, 700 meter of melt. And then all these dots and symbols here show you the variety of minerals that argue for the presence of liquid water on Mars. And so, I'm not too sure about the statistics here, but I'll show you some stuff a little bit later. But you can see that this is the map that we get, all right? So basal melting is possible. And there are at least some places where we should be able to figure out whether, if there was a causal relationship between what we see and what we predict from this map. So the one place that is extremely high, where we get extremely high melt prediction, is this place again called the Terra Serenium, Terra Cimmeria. There are some other places as well. So these are all places that have significant amount of thorium and potassium, right? So these are places where via gamma ray spectroscopy, we are finding that the surface and perhaps the subsurface as well contains anomalous amount of thorium and potassium on Mars. So which means that, there was some sort of process responsible for enriching these places in thorium and potassium. And it's also great because, these elements, like I said earlier, are heat producing elements. And there are also within this region I'm showing you this 4 triangle. And so the 4 triangle corresponds to these massive basin. They're called the Aridania Basin. And after we wrote the paper, we found out that people had looked at this region. So the 4 sort of basin that I'm showing here are the same areas that I'm showing here by the 4 triangles. And so it's called Aridania Basin. And it's really fascinating because before our paper came out in 2017, some of the other authors, they had looked at this region and they had found out that there should have been this massive internal ocean or sea on Mars at this place. So much so that they estimate that the volume of water in this one region could have exceeded all the other known lakes on Mars. Okay, so there's substantial evidence that, in the same place where we see this massive amount of uranium, thorium, potassium also was a site of a massive inland sea called Aridania. And the authors that published this paper, their view of how this place came to be is very similar to what we had been pushing on this paper, where you had this ice cover, right? Because Mars was primarily icy and cold, but then you had this liquid water generated in the subsurface simply because of heat related to the planet's internal heat. So that's basically what it's shown here. And so, so that makes sense for this place, right? So these triangles, again, this is where this Aridania places, but we wanted to see kind of like a more general statistics. And so we created what's called cumulative distribution function plot, ACDF plot, from these the places where we see all these kinds of different minerals to see if there's any robust relation there. And this is what we see. So all of the Noachian terrain has a cumulative probability. So the x-axis is the heat flow, the y-axis is the probability, and you can see the cumulative probability of all the Noachian terrain. But then one mineral that is really diagnostic of like, groundwater is chlorides. And with chlorides, what we find is that the places where chlorides form on Mars tend to have significantly higher heat flow than the average Noachian terrain. So you can see the difference between these ECDF plots, the blue one and the dashed yellow. And so this at least provides a preliminary ammunition to the idea that most of the water in Mars's past, formed perhaps from basal melting rather than this atmospheric top-down melting. Okay. It's also fascinating because a lot of these regions that are enriched in potassium and thorium are super magnetized. And I'm not going to go too much into what this means. It's a paper that's currently in review, but it's really exciting because, again, so the background here is the crustal magnetic field. Once upon a time, Mars had a magnetic field, and the record of that is preserved in the rocks. It's called paleomagnetism, and so this is the radial magnetic field, and this is the same map, but with the thorium-enriched region, right? And so we're finding that, again, this Terra Cimmeria, Terra Serenum region is not only super enriched in uranium, thorium, potassium, they also have the highest amount of chlorides. They also were probably the site of the largest inland sea. But now we're finding also that, hey, this is also the place where, not only do you have this super, super high magnetic field, orders of magnitude higher than in other planets, right? Preserved there, but also that the same place happens to be enriched in these elements and other geochemical factors. And this is important because we still don't have first order idea about how Martian rock got magnetized. Was it through cooling or was it through some sort of geochemical reaction? And so there's this other idea, which is that most of the southern crust retains that magnetic signature via a chemical reaction called serpentinization, which is something that happens when you have hot water interacting with rocks, which is what we're finding now. And so there's this really interesting idea now that, even most of the magnetic field could have had its origin tied to the sort of hydrothermal reaction. So anyway, so the key takeaway again is that, again, remember, we're trying to ascertain basal heat flow, the surface heat flow from a planet that's 47 million miles away at 4 billion years ago. And so, any measurement, any sort of, model assumption, they have caveats, there are uncertainties. And so the point is not to accurately predict the surface heat flow, but the point is really to say, given what we understand about basal melting, was it possible on Mars? And what we show here is that basal melting by geothermal heat is totally plausible, completely plausible with like what we currently know about the Martian geochemistry and geophysics. And, again, we're not saying that, this is the state of Mars and, this is how Mars got liquid water. But the point again here is that the Finch-Youngson paradox has remained there for about 40 years. The paradox plagues Earth, Mars. It has its own really cool implication for Venus and Mercury, but nevertheless, it has plagued the field for a while. And what we show here is at least what I can say is a partial solution, if not a complete solution, to the paradox on Mars. And, if you think about the planet Mars, even if it was, this like utopia that we tend to imagine with like liquid water on the surface and Martians, swimming and whatnot, over time with the loss of magnetic field, over time with the drop in global temperature, the atmospheric thinning, the only place where you could have had stable water is deep in the subsurface. And there, processes that I'm talking about here, where you have heat being generated inside of the planet, would have been the only way to stabilize that liquid water. So even if Mars was completely, full with water on the surface, this is still important because over time that water was not there. And the only habitable region was deep in the subsurface. Right. And so the one thing that we're trying to do is understand the depth to where that water could have circulated right now. This is some future work we're doing because this is called critical zone on Earth, and really an insight into how deep could you have had this water go on Mars's past depends on this critical zone. So we're basically taking Martian simulants, like these simulant grains, and we're compacting them to see how deep could you go. And we're also finding that a lot of time, actually, you can just make a complete rock. You don't need heat, or you don't need pressure. You don't need water. You can just compress it and you can make rocks. So again, I think I'll stop at that, but I hope you got something out of that. And those of you, involved with the Mars missions and whatnot, I would say maybe, keep a close eye on Terra Cimmeria region, because I think that place is really weird and enigmatic in the good sense. So I'll stop there, and I'll stop sharing my screen and take any questions, and I'll leave this code there.
Thank you very much. This was great. Yeah. Maybe I could just ask a question. It's really not a very sophisticated question. Your talk was very clever. You used many ideas to do something that I would have thought would be impossible. The ideas such as the bending of the lithosphere, I think, is a very clever idea, which I had never heard of before.
Yeah.
But I don't know what kind of uncertainty you have on your conclusions, given that you have many constants, many models and things like that. It would be nice to get your perspective on how, let's say, robust these conclusions are.
Yeah, so again, right, I mean, all we're trying to really ascertain is, what's basal melting possible, right? And so the number one factor that really either makes it or breaks it is the surface heat flow. If you had surface heat flow higher than, let's say, 100 milliwatts per meter square, which is actually very, very likely on early Mars based on our understanding of how the Earth has evolved, regardless of what the other parameters value were, you would have definitely gotten, you definitely would have had basal melting happen on Mars. In fact, the basal melting idea is even invoked today. So there are a lot of papers that have recently come out about the detection of subglacial lake in the south polar cap of Mars, right? So I don't know if you've seen this in the media, but there's a team from Italy that have looked at the radar reflection from the South Pole, and they've found these what looks like to be liquid water lakes reflecting. And so the only way to make that on Mars today is also geothermal heating. And so if those measurements are correct, then we know that Mars in the south polar cap needs at least about 70 milliwatts per meter square of heat flow to have this subglacial liquid water. And again, by virtue of this radioactive decay, the heat flow in the past would have been higher. And I think there's a very good chance that we should see basal melting happen. And the other thing is also, we don't even have a first order estimate of how thick the crust is, right? I mean, we don't have, seismically derived crust yet. Yeah. So I think these things are going to, without even a comprehensive understanding of uncertainty of those parameters, you're just going to be propagating error if you're trying to put uncertainty bounds on something like this. So all I think I would like to say, and all of people that are hearing this, I would say, take it with a grain of salt, but I think the first order estimate is probably good, and we need way more estimate to really say that basal melting is the way to solve the Faint-Yongson paradox on Mars.
There are two other questions for you. Tamara, can you let them in? Charles Lee and Robert Johnson?
Sure.
One at a time, probably, yeah.
Yep, here's Robert. Oh, second Robert's gone. Hold on.
Yeah, Charles may be there. So.
Charles,
can you hear me?
Yes.
Yeah, I just wanted to know, since so much effort has been put into model atmospheres, has anyone modeled the atmosphere for the dry for your model? I mean, there's certainly nitrogen present and other things. So.
Yeah, so there has been all kinds of models that have been presented, atmospheric models for Mars. I mean, both assuming that it was warm and wet, saturated up to 2 bar with CO2 and H2O, but also, models that say that, the paleo pressure was actually substantially lower than that. Like let's say 34 millibar or 6 millibar. So there's a range of models. There's a range of models with exotic greenhouse gases to really, 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 really tenuous atmosphere. And the end product from those models result in, either Mars being this icy highlands or this, utopia of water.
Great.
No, but I mean, you can still have Titan has a robust nitrogen atmosphere. So would something like that be on Mars? And
I'm not.
it's cold enough.
Yeah, I don't think I've seen a model with just nitrogen. I think most of the models that I've seen, these sort of like 3D climate models, they're mostly concerned with CO2 and water in the atmosphere being the prime agent.
Great. Charles, did you want to ask your question?
Oh, yes. So thank you very much for the excellent talk. So I would like to ask, I'm not a planetary scientist, but it's just a very general thinking. So is the basal melt model consistent with for example, the variation in the density of the channels on the Martian surface? Like if there's more water, much more water, there could be higher internal density. So can the basal melt model explain the variation in the channel density? Thank you.
Yeah, that's an excellent question. That's a paper that a postdoc and I am currently writing, where so in this model, what we do is we say, okay, is basal melting possible or not? But the one advancement that we do in this follow-up work is once you get the basal melted, what happens to the basal melt? And so we sort of use landscape modification routines to see where the water would go and how much water would you need to create these channels, and then compare the simulated channels to what we see in Mars. And in general, we see, again, that there could be, it's very easy to lie with statistics, right? And I think, depending on like the statistics we present, I mean, one can either make a claim that, yes, it explains the density of the valley networks, but there's caveats because a lot of the smaller valley networks on Mars have been eroded over time. And so what we see are really just like the bigger, wider valley networks now. And it's, I think there is some, but that's a work we're currently undertaking. And if you ask me in about 2 months, I should be able to give you a better answer, but that's really a great question. And yeah, that's something we're actively looking at right now.
Yeah, thank you. Looking forward for the answer.
Awesome.
We have one last question from Danny. Danny, do you want to ask Luju directly? Okay, so Danny.
I can read out the question if he's not there.
No, he's here, but
Okay.
But for some reason his mic isn't set up. So do you want to
So
read it?
I'll read it out anyway.
Okay.
If he can't.
Yeah.
Going back to your map of minerals measured by remote sensing, is there any reason as to why the northern plains don't have many points for minerals other than the subsurface ice reducing the certainty of observations? That is that due to observation limitations or just that there haven't been many observed?
Yeah, no, that's a great question. And so the answer to that is something that is that has to do with a fundamental property of Mars, and that's called the hemispheric dichotomy. So what happens, what you'll find on Mars is that the southern hemisphere of Mars is higher in elevation. It is much more cratered. That's where you have more magnetic field. And the northern hemisphere, we think that once upon a time used to perhaps look like the southern hemisphere, but the northern hemisphere is substantially younger. So one idea is that about 4.4 billion years, or maybe like a couple of 100 million years after the planet formed, that there was this massive impact that removed much of the northern hemisphere. And so what you see when you look at the northern hemisphere is, again, not the same old primordial southern hemisphere surface that we see. It's actually much younger. And so, there could have been just as many, minerals in the northern hemisphere. There could have been this magnetized region, just like we see in the southern hemisphere, but most of that has been eroded. Most of that is gone, and the reasons for why that could have happened is there's a range of reasons. It could be exogenous, like one impact crater or multiple impact craters. There could have been what's called the mantle convection. Or there's even an idea that early Mars had Earth-like plate tectonics. And so most of the northern hemisphere actually went underneath the southern hemisphere. And those record of mineral diversity, of the magnetic field diversity, et cetera, has been completely lost, much like the ocean plates, right? Because they have a mean lifetime about a couple 100 million years. Everything gets subducted. So that's really the reason why you don't see as many mineral points in the northern hemisphere. It's also really dusty.
There are three more questions. Maybe there's one more question. But after this, we should close the talk. There is one from Rasha Abdul Rahman.
Do you? Oh, go ahead. Can you see it, Luju, or would you like me to read it?
Let's see. I'm trying to open the Q&A.
So it says, do you think statistical method ML will help to estimate snow depth or water vapor or soil moisture using raw RS data?
I'm not sure what ML is.
Let me get Rasha on here.
But I think the issue would be to measure the snow depth and soil moisture 4 billion years ago, right? And I think that's really going to be the problem. Like right now, we could probably, yeah. We can definitely measure the soil moisture. Phoenix spacecraft measure the near surface moisture. But to answer something so fundamental about Mars 4 billion years ago, I think the best way to do any of that would be some sort of direct drilling like we do on Earth, I would say.
Okay. I think we should close the session.
Okay.
Thank you very much, Dr. Ojha, for this wonderful talk. I'm sure, like me, the audience enjoyed it. We appreciate you taking the time for doing this. Thanks a lot, and all the best to you for your future publications.
Awesome. Thank you very much for having me. And again, good luck, everyone.
Okay,
and,
great. Yeah, thank you. Thank you all for being here.
Awesome. Take care.
Thank you.
Okay,
Bye-bye.
bye.